Hey guys, welcome back to our YouTube channel. So today we are at a hands-on session for optimizers in neural network. So last few classes we have developed some theoretical understanding of the neural network optimizers, starting from gradient descent, stochastic, mini batch, momentum, then RMSProp, Adagrad, and finally Adam. So we have looked at various options. Now what we are going to see is that how we can choose these different options from our TensorFlow and Keras framework. That is number one. And also we are going to look at it on a data set, on a classification problem. And this we are doing in our Jupyter Notebook framework or Jupyter Notebook environment, which is hosted in Kaggle. Available as a public notebook, so you can change the code, run and learn from it. Okay. All right. So let's start by importing the libraries. So we are just going to need TensorFlow, Keras, NumPy, Matplotlib, and Pandas. Okay. Then what we are going to do is we are going to import the data set. Okay. So for that we are going to use keras.dataset. So we have a very famous data set called as Fashion MNIST. Now Fashion MNIST is a data set which is very similar to your traditional MNIST. So it has 10 classes, and the inputs are also image of size 28 into 28. However, it is not handwritten digits but some of the fashion items. Okay, so that's why the name Fashion MNIST, and it turns out that Fashion MNIST has more diversity than your traditional MNIST. So as a result, it is accepted as a better test bed. Okay, so let's import this quickly. Okay, and after that let's assign the class names. The class name is not available. Okay, so you will see that we have used a function called as load data, which is already there. Okay, with the data set, and what happens is that it creates beautifully this training set and testing set. So these train images are your training observations and train labels are the corresponding labels. Okay, same goes about test images and test labels. Now let's standardize the input. So if you don't standardize the input, neural networks really do not learn well or learn correctly. So here standardizing is very easy because you are dealing with pixel values. So max mean value is 0, max value is 255. So you can directly divide by 255. Okay, so this is real quick and easy, and you apply for both train images and test images. If you would like to look at image of some of them, all right, so these are, as I said, the inputs are images. You can quickly plot them. Okay, and plot map that we are going, the color map that we are going to use is binary. So it is going to give you images of some starting 10 items of our Fashion MNIST data set. So as we expected, so these are fashion items. So you have ankle boots and t-shirts and dress and etc. Okay, all right. So now let's go ahead and create the model. Okay, and if you remember, Keras builds a sequential layer where you add the layers one by one. So as it is an image, the first layer is a flattening layer. So you say the input shape is 28 into 28, which converts it into a 784 into 1 feature vector. Then you are using a hidden layer, okay, with the activation ReLU, and finally you have a dense layer. So this dense layer actually has 10 neurons because you have 10 classes. Okay, so let us run this quickly. Okay, so all the models are created. Okay, so basically there is no change in the models, only that we will run it with different optimizers. So identical 5 models we have created with 5 names. Okay, now let's compile the models. And now when we are compiling the models, you will see that we are using the optimizer. So we are going to run the experiment for Adam, RMSProp, Adagrad, SGD, stochastic gradient descent. So we are also going to look at stochastic gradient descent with momentum. So that is not directly available. This option is not directly available. So actually TensorFlow and Keras is a very, very flexible framework. Okay, so what you can do is you can create an optimizer object. Okay, so basically you are directly using something like optimizer Adam, but a lot of things are happening behind it. So you know that there are different parameters like learning rate, beta 1, beta 2. So you don't really need to worry about this because these are initialized with good tested default values. Okay, however, the SGD is initialized with momentum with 0. So that's the reason we are actually creating one option with this particular optimizer where momentum is 0.9. Okay, so now let's go ahead and fit the model. So the fitting of the model will take a little bit of time. So first we are starting with stochastic gradient descent. So while I'll make it run, let's discuss a little bit about stochastic gradient descent. So you know that how it is different from gradient descent is on which observations it is calculating the gradient. Okay, so in SGD you calculate the gradient on one observation, so it is very memory efficient. But what happens is, as a result, the gradients that you calculate are quite noisy. Okay, because it is not very smooth, because for each observation you are calculating the gradient. So somewhere it can be positive, somewhere it can be negative. So there can be a lot of fluctuations. Okay, and we have also discussed that it needs less memory, or not only less memory, it is less prone to get stuck in local minima. Okay, now what we are going to do is we are going to look at momentum. Okay, so let me again run this. Okay, and then further discuss it. So as we said that if some curve is noisy, so one of the thing that we many times do is that we actually smooth the noise, right? How do we smooth? We take an average. Okay, so taking an average is often called as moving average. And if we give equal weight, okay, equal, or we treat all the observations equally, right, which you are calculating the moving average, it is unweighted moving average. If you assign a weight, then you call it as a weighted moving average. And momentum actually brings this effect of exponential moving average. Okay, and so it will give you good result. However, I am not sure if it will be evident on the run of 10 epochs, because 10 epochs is really very less. And if you look at the different values to start with, okay, so you'll see that there is a gradual increase that is happening. Okay, but however, even with the gradual change, or gradual increase with the epochs, it is not saturating, right? So it can run for many epochs actually. Okay, let's now look at the next optimizer. So we are looking at Adagrad. Again, let's run and then discuss. Okay, so Adagrad is actually talks about adaptive learning rate. So what it does is it actually changes the learning rate. So as you go towards the optimal value, you slowly change the learning rate. Okay, and that depends on taking the square of the derivatives and dividing that by your learning rate. Okay, and one of the problems with Adagrad is that it will actually slow down as you move from epoch to epoch. So learning can really slow down at one point of time. And one of the very extremely important advantage of Adagrad is that it allows the neurons to learn at a rate of their own. Okay, so this is one of the very important advantage that appears to me. Okay, so this is Adagrad. Adagrad also, you see, it started from 77 and moves up to 84. Okay, now let's look at RMSProp. So as we were saying that uh, your Adagrad has some problem where the learning rate can grow, come down to 0, right? Especially for features which has a lot of variability. Okay, so in that case, what RMSProp does is somehow breaks that decay, right? So how does it do it is, again, it goes back to the concept of exponential moving average. So earlier when we are applying the exponential moving average, it was applied on the numerator. So here this is applied on the denominator. And like all other optimizers, okay, you will see that it is going from moving from, like, it started from 82 and then slowly it is going to 90%. So as we were discussing, that RMSProp is one of the better optimizers. So you can see even for 10 epochs, probably that is little bit evident. Again, let us run the Adam optimizers and then discuss. So it combines both the idea of RMSProp and momentum, right? So RMSProp applies RMSProp actually applies to some kind of smooth the decay of the learning rate. Okay, and momentum actually smooths down the gradients. Okay, so it has two smoothening effects. All right, and momentum actually Adam actually is probably the most flexible optimizers. Okay, so it also, you see that it has very promising result as was for RMS props. All right, now let's plot the accuracy over epochs. Okay, so this is we are just going to have this from the history. So this history actually is kind of a dictionary object where you are having these accuracy values and loss values. So whatever you are seeing in the result, this will be available in this history object. And what we are going to do is, for like convenience of plotting, we are going to add them in a pandas data frame and plot the same. Okay, so let's take the accuracy of all the 5 models that we have discussed earlier. Okay, and now let's create the data frame and give them the suitable names. Let makes the epoch column the index of this data frame. Okay, now let's plot it. Okay, so if I plot it, you see that only SGD with momentum didn't give you good results. So I'm sure if you run it for more number of times, it will give you quite good result. And the best one are your Adam and RMS. Okay, which actually went over 90%. Okay, let's now validate our test set. So we are starting with Adam. Okay, so Adam is giving you an accuracy of 88%. So let's remember this value. Let's look at RMS. Okay, so RMS gives you 86.94. So Adam is winning right now. Okay, and then let's run for uh, Adagrad. Okay, so let's again quickly run this. There is a small mistake. It should be test levels. So if I run this, it comes to 83.09. Okay, so still Adagrad is winning. And then let's run on SGD, okay, which is the stochastic gradient descent. It is 85.48. So you will see that you cannot really generalize from your training data, right? So from SGD, Adagrad give a better result probably. Okay, however, this is the SGD and this is the Adagrad. No, SGD actually performed better than Adagrad. Okay, and let's look at also. So let us add the code for SGDM. Okay, and SGDM is expected not to give a very good value on the test set. Okay, because we saw that even on the training set it was not giving a very good value. Okay, so it is much lesser. It is only 66.5%. Okay, now let's try to continue with the best level. So far what we have achieved is best result was our Adam optimizer, 88% on the training data set. Okay, now let's continue it for some more time. Okay, and let's see the result. All right, so let's run it for some more epochs. Okay, and let's see how. So you will see that it is continuing from where it started. So it is starting directly from over 90%, and then it is proceeding. There is slow amount of improvement, not so fast improvement as it was happening in case of when we are running it for the first time. And actually these models, remember the weight, so that was the reason we created 5 models. We did not use the same model by changing the optimizer option. Okay, and if you see, we already 9 epochs are completed and we are around 93% already. Okay, and still it is increasing, and at one point of time we will see that it will quite come down. And why we don't let it run forever is that then it will start overfitting. Okay, so still it is increasing. Yes, so it crossed the 94% marks, and finally it will end maybe around 94.5, 94.08. Okay, now let's look at how this model is doing on our testing data. Okay, so let's run this. So actually what we have done is we have found out that Adam is the best optimizer. So we have let it run for more number of iterations. So there is not much improvements actually. It is 88.65. Earlier it was 88.23, so around 0.4% we have gained, okay, because it has probably started overfitting. And if we train our model for more times and in continuously validate it on testing set, we'll see maybe we'll cross the 90% marks. Okay, so in today's notebook what we tried to do is we try to give you a good understanding of how to implement different optimizers using this TensorFlow and Keras framework. And we have run on this Fashion MNIST dataset. Okay, and we have tested on 5 optimizers. We have seen that Adam has given us the best result on test set. So what we have done is we have picked up that model and run for more epochs and have improved our testing set accuracy by a 0.4%. Okay, so thanks guys for watching this video. If you find this useful, please like, subscribe and comment, and please do run this notebooks. This is very, very important. Unless you do it on your own, you will not internalize the concepts that we have discussed in the theory class. Thanks so much guys. Thank you once again for all your patronage.